Now I am.
Thank you.
So let me just review this just for the benefit of the tape. So problem session 12.1. So I'm defining a homomorphism. So a homomorphism is a function from a group to a group which satisfies this condition. F of x1, x2 is f of x1 times f of x2. What this really means is whatever is the operation in G, you take x1 and x2, you multiply or add them depending on what the operation is in G. You look at f of x1 times f of x2, those are elements in G prime. You multiply or add them, or you do whatever is the binary operation in G prime, and you have a homomorphism if this condition is satisfied. I should really put maybe a little symbol here. This dot just means whatever is the operation. Could be multiplication, could be addition, could be something else, doesn't matter. This is the operation in G, this is the operation in G prime. And this is a homomorphism. Now, an isomorphism is a homomorphism, that means satisfies this, that is also one-to-one and onto. So an example of a homomorphism is the following. I take R, is the additive group of real numbers. I take R star to be the multiplicative group of the non-zero real numbers. And I define a function from R to R star by exponentiation. F of x is e to the x. So what does it mean to have a homomorphism? If I take two real numbers, x1 and x2, and I operate on them in R, that means I add them and apply f to that, I get this. This is f of x1 in R star, f of x2 in R star, and the operation in R star is multiplication. So this is exactly the functional equation that defines a homomorphism. I mean, that's exactly what it is.
I have a question.
Don't be confused by the fact that you can also multiply real numbers. That's completely irrelevant. Here I'm looking at R as an additive group. I'm not going to multiply real numbers. When I'm in R as an additive group, I can only add them.
Okay. So to clarify then for homomorphism, G and G prime could be different types of group. One could be additive, one could be multiplicative. Is that also true for isomorphism, or do they both have to
yeah,
be
absolutely. And I had written down, in fact, the four possibilities here, right? So in the case of an additive group into a multiplicative group, this is the functional equation that defines a homomorphism. If G is additive and G prime is multiplicative, it's this. And that is exactly what we have here. Exactly.
So why is this not isomorphism?
Well, for one thing, it's not onto. F is not, exponentiation is not onto. F of x is never equal to -1.
But you're doing it to the positive numbers, Professor.
Excuse me?
You're defining the R cross as only the positive numbers, right? So then it is
multiplicative group of, what is this word?
Oh, non-zero. Okay.
Yep. If I made this the positive numbers, this would be an isomorphism.
Okay. Okay. I thought it was only positive numbers. Okay.
Okay. Now this function has a kind of an inverse. Suppose I define a function g from the non-zero reals under multiplication to the all reals under addition by g of x is log of absolute value of x. So the log of the absolute value is defined for non-zero numbers. The graph looks like this. And here the operation is multiplication. If I take two numbers, x1 and x2, and I multiply them, what is g of x1, x2? That's the log of x1, x2. they teach you in pre-calculus the log of the product is the sum of the logs. So this is g of x1 plus g of x2. So in the additive group of reals, we have exactly the right equation. So this is also a homomorphism. Now, this function g is onto, but it is not one-to-one. Because, for example, g of 1 is 0 and g of minus 1 is 0. Okay. Actually, if you like examples from calculus, here's another simple example. Suppose we take g, I'll write this as z square brackets t. This is all polynomials with integer coefficients. So you might have a polynomial, a of x equals 2t cubed plus t minus 17, and b of t equals t to the 10th minus t to the 8th plus 7 t squared plus 11t plus 100. Right? These are polynomials with integer coefficients, and you can add them. You get t to the 10th minus t to the 8th plus 2t cubed plus 7t squared plus 12t plus 83, I think. And you can subtract them. So this, you can check, this is an additive abelian group under addition. You can add and subtract polynomials. The identity is the zero polynomial. Right? Very nice group, lovely group. Here's a function from g to itself. So define a function from the polynomials to the polynomials by differentiation. F of a polynomial a of t is the derivative. Now, this is a homomorphism. For one thing, if you take a polynomial with integer coefficients and you differentiate it, you get another polynomial with integer coefficients. So for example, for this polynomial, f of 2t cubed plus t minus 17, the f of this is the derivative. That's 6t squared plus 1. This is another polynomial with integer coefficients. So differentiation is a homomorphism on this set of polynomials. Yeah. It's not one-to-one, and it's not onto, but it's a very good homomorphism. So this function is f is not one-to-one or onto.
Oh, why is it not onto? Because a constant cannot have a cannot be integrated. Basically, integration of constant won't be there. Is that one?
Well, no. I mean, if you have for every integer c, which is a polynomial, constant polynomial,
Right.
f of ct is equal to c. So you can certainly get every integer.
Right. You can get c in the range, but
But the polynomial a of t equals t is not f of a of t for any polynomial, right? Because what polynomial when you differentiate it gives you t? Well, a half t squared, but a half is not an integer, so it's not in this ring.
oh yes, understood. So for the between holomorphism and isomorphism, if you restrict the group to the range of the function, would that be isomorphism always, or it's not always true?
It depends on whether, only if the function is one-to-one.
Before you go on, can you go back to the last page?
Yep.
I'm just confused because not this page, the page with the polynomials, because I thought that what we were doing was we were looking at a X and a Y when we're looking at homomorphism or isomorphism.
Well, X and Y are just letters.
No,
It's
I know,
just
I
like
get
in
it.
calculus, you have a function. You can call it, sine X, sine theta, sine T. It's just a variable.
No, I understand. What I'm saying is that in this case, now we're looking at polynomials. We're not looking at two separate things that when you take the product of it or when you add them together, you get what, that criteria, like f of x plus y equals f of x times f of y. We're not looking at that. So I'm confused.
So, in calculus for all functions, I'll call them, a of t and b of t. You learn that the derivative of the sum of two functions is the sum of the derivatives. Right? This is calculus, right? The derivative of the sum of two functions is the sum of two functions. This says exactly that if f is the function differentiation, then the derivative of the sum is this. This says exactly that differentiation is a homomorphism in the group of polynomials, actually in any group of functions.
Doesn't the sum have to equal the product for homomorphism?
No. Again, everyone's getting confused about the symbols. So let me start again. Suppose G is a group and the binary operation is denoted by a star. So now I'm not going to use addition or multiplication, I'm going to do star. So, and suppose G prime is a group with a binary operation, I'll denote it by a circle, little circle. So if you have X and Y if you have X1 and X2 in G, then the way you add, then X1 star X2, that is their sum or product, whatever you want to call it, that's also in G. And if Y1 and Y2 are in G prime, then their sum or product, or whatever is the operation, is Y1 circle y2 in G prime. A binary operation says to every two elements you associate a third. So get to x1 and x2 is x1 star x2. If this were multiplication, it would be x1 times x2. If this were addition, it would be x1 plus x2. I'm just using star to denote the operation. So F from G to G prime is a homomorphism if for all x1 and x2 in G, if I take x1 and x2 and I combine them by the binary operation and apply F to that, I get exactly what I would get if I went from x1 to f of x1 in G prime, from x2 to f of x2 in G prime, and then I perform the binary operation in G prime. So these symbols, they could be addition, they could be multiplication, they could be some other bizarre binary operation. This is the definition of a homomorphism.
So let me get clear. So they don't necessarily have to be the same. They could be the same, or they could be the same they could be the same operation, or they could be different operations.
Yeah, they can both be addition, they can both be multiplication. One can be addition, the other can be multiplication.
As long as that binary operation is defined in G prime.
Well, you don't have a group if you don't have a binary operation.
No, what I'm saying is that, like the example that you gave with e to the x, you stated for G prime that the binary operation was multiplication. For the e to the x example that you just gave?
Yep.
Right? So pretty much we have to use whatever binary operation is stated for G prime.
Well, there's nothing else you can use. When you have a group only has one binary operation. If I give you the additive group of real numbers, you add them. You can say, well, but I can also multiply them. And the answer is no, you can't. That's irrelevant. It's like it doesn't exist. If I'm looking at R as an additive group, all you can do is addition.
Okay. All right, so with the polynomial, so let's get back to the polynomial example.
Yes.
Do you necessarily have to specify what's the binary operation?
I did.
But for G prime as well?
It's addition.
If I'm taking the polynomials, this is a group, this is only a group under addition. This is not a group of, you can multiply polynomials, but for us that is irrelevant. If you take the polynomials, there is a binary operation of multiplication, but with that operation, you do not have a group. So I'm looking at the polynomials as an additive abelian group. I'm not multiplying polynomials here ever.
Okay, got it. Professor, there was one question in homework. That was, I think it said something like, prove that Q is not a cyclic group. So would it be because, let's say if there was a generator, if you take any fraction of the generator, that has to be in Q, but then that fraction cannot be generated using that generator?
So I think someone asked me that problem yesterday, but let me go through it again.
I mean, you don't have to do it. I mean, that
All right, well then I'll just say really quickly. So suppose you take a rational number.
Right.
It's like R over S, it's a fraction.
Right.
If you look at all multiples of that fraction, you only get denominators which are S or divisors of S. You won't get any number whose denominator doesn't divide S. So for example, if you take any prime that doesn't divide S, the fraction 1 over P can never be represented as an integer multiple of R over S. So no one fraction can generate the rationals as an additive abelian group.
So can you actually critique this logic though? I mean, I started with contradiction, saying that, let's say there is a number P that belongs in Q such that, it generates everything. Then because P is in the Q, P over 2 is also in the Q, but then the generator
no. Yeah, go ahead. All right.
Then if the P has to generate 1 over p by 2, then the multiplier is 1 over 2, which is not in z, but which means that it can't generate a fraction of itself.
Okay, that's fine. If you write it down
would that
carefully,
logic
that's
work,
okay.
or is it wrong?
What?
So I was saying, would that logic work, or is there a
Well,
flaw
it's
in
not a
that?
question of whether the logic works. It's a question of whether you can write it down carefully and completely and exactly. Well, let me just go back and say a few more words about homomorphisms. So if G is a group with identity element E, and G prime is a group with identity element E prime. So this is actually a little theorem, if you like. If F from G to G prime is a homomorphism, that implies that F of E has to be equal to E prime. And if I apply F to the inverse of any element, that's the inverse of F of X. So every homomorphism satisfies these two properties. And the proof is very simple. So I'm writing everything multiplicatively. That's the best way to do it. You know, if you have E and you multiply it by itself, you get the identity. So F of E is F of E times E, because these are the same. And by the property of being a homomorphism, this is F of E times F of E. Now, I don't know what F of E is yet, but whatever it is, it has an inverse. So multiply this equation by F of E inverse. I get F of E inverse times F of E is equal to F of E inverse times F of E times F of E. But when you and this is a multiplication in G prime, right? F sends elements of G to G prime. So an element times its inverse is the identity. And this, by associativity, is F of E inverse F of E times F of E. This is the identity, so this is just F of E. So therefore, F of E is always E prime. A homomorphism always sends the identity to the identity. And the proof of the second statement is equally nice. For any X, E is equal to X times X inverse. So F of E is F of X times F of X inverse, which is F of X times F of X inverse. But of course, F of E is the identity. And the identity is also X inverse times X. So E prime, which is F of E, is also F of X inverse X, which is F of X inverse times F of X. And if you put these two statements together, what does this say? If you take F of X and you multiply it on the right or on the left by F of X inverse, you get the identity. And it follows that F of X inverse is F of X inverse. Right? This element is the inverse of F of X. F of X inverse is the inverse of F of X. So these are important properties of a homomorphism, and they're very fundamental.
So this is what you had used to prove the Kleiner 4 group, and Z mod 4Z is not congruent, right? Sorry, not isomorphism.
I think so.
Okay, thank you.
Well, okay. Anyway, we have an enormous amount of material to do in the next month, which means by next Wednesday. So I urge you to spend a lot of time reading the topics and group theory lecture notes, which every day get bigger and bigger because I'm adding stuff. I think I've already posted homework problems for Monday.
Professor, can you just take a couple of minutes to review what's coming over next week?
Yes. So I define groups and homomorphisms and isomorphisms, and I constructed examples of matrix groups and permutation groups and various abelian groups. But we've proved almost no theorems so far about groups. And so what we'll be doing first are basic theorems, facts about groups. And then I'm going to also introduce rings, and there'll be a few basic elementary examples of rings and theorems about rings. So more groups and a little bit about rings is what we have left to do in this semester.
Thank you.
Okay. I guess that's it then. I will be back online at 4 o'clock. Let me remind you, I posted this on Blackboard. On Monday only, the problem session, instead of being from 11 to 12, will be from 12 to 1. I can't be here at 11. So on Monday only, the morning session is at 12 o'clock. Everything else is the same. Okay. All right. Bye, everybody.